This is my Calculus 1 course. Today we're going to learn antiderivatives and indefinite integrals. If you haven't done the homework completely and correctly from last class, do that homework before watching this video. So what we're going to do today is it's not going to seem to be really related to what we did in the previous classes. But we're going to find out in the next class why antiderivatives and indefinite integrals are related to the concepts we've learned so far in integral calculus. We're going to need the differentiation formulas that you see here. You should be familiar with most of these formulas, but I would recommend taking a picture of these formulas for this class, because you're going to need not only to know the formulas, but also to know the Roman numerals that I've written here that tell you which formula we're going to use. So for most of this course we've been learning how to, or a large portion of this course we've been learning how to find derivatives. But now we're going to learn how to do the opposite operation, which is antiderivatives. So it's easier to give you an example here rather than to go over definitions. So first, let's find the derivative. We know how to do that. We just use the power rule, so we have 3x to the second power. Easy. But now we're going to find something called the antiderivative. The antiderivative is a function that we're going to find, or actually we're going to learn that it's a family of functions, a group of functions, such that when you find the derivative of that function, you get the original function that we started with. And I bet that you can probably find that function on your own. If you stop the video and take a couple minutes, you can probably figure out what that is on your own. So if you want to, you can see if you can do that. You don't have to do it, but notice that the exponent is reduced by 1 when we find the derivative. We subtract 1 from the exponent. So if you go in the opposite direction, we should add 1. So we know we're going to have x to the 4th power. But now let's check something that is something that makes it very easy for us to find antiderivatives is we can constantly check our answer. All we have to do is find the derivative of this expression, and if we get the original expression, then we know we did it correctly. So let's find the derivative of this. If we find the derivative of that, we get 4x to the 3rd power. So we didn't quite find the correct antiderivative, but we do have the right exponential or the right power expression here. We just need to somehow get rid of this 4, because we don't want a 4 in front of x cubed. Now, the power rule tells us that we bring this exponent down in front and multiply it into the power expression. So if we want that 4 to go away, we have to do the opposite of multiplication, which is division. So we have to have a 1/4. Remember, multiplying by 1/4 is the same thing as dividing by 4. We have to have a 1/4 there to counteract the 4 when it comes down. So now let's find the derivative of 1/4 x to the 4th power. So we're going to use the constant multiple rule, which tells us when you have a constant times a function and you're trying to find the derivative of that, the answer is the constant times the derivative of the function. And notice when we multiply 1/4 and 4, we get x to the 3rd power. That's what's left over. So this up here is what we call the antiderivative of this function. We went in the opposite direction. Again, we know how to find derivatives. We've done that. The derivative of x to the third power is 3x to the second power. But the antiderivative is 1/4 x to the fourth power. But there's something that we need to do to modify this expression so it represents the correct expression, and that is we need to add c. Now, what in the world is c? Well, c is a letter that represents any constant you want to put in there. Now, let me show you why we have to add some letter that represents a constant. So let's say that you have the function, we'll use g, I guess. Let's say g of x is equal to 1/4 x to the fourth power plus 3. Let's say that h of x, a different function, equals 1/4 x to the fourth power minus pi. Pi is just a constant, right? So if we find the derivative of g of x, we get x cubed. The derivative of 3 is just 0, right? If we find the derivative of h of x, we get x cubed again. Again, the derivative of pi is just 0. So that's why we have to add c that represents any constant, because we don't know what that constant is going to be, but we know that there could be a constant, and c could be 0. That's fine for c to be 0. But there has to be some letter there written that represents some unknown constant. So I know that's kind of weird, but the antiderivative of a function is actually a family of functions. We can have 1/4 x to the fourth plus pi. We can have 1/4 x to the fourth plus a trillion. We can have 1/4 x to the fourth minus 72.9. There's an infinite number of antiderivative functions that are functions where if you find the derivative, you get back to this function here. So that's why we're asked in this problem to find the derivative of each function and then find an expression representing the antiderivatives of the function. So there's actually more than one antiderivative. There's actually an infinite number that you could find. And notice that we use a capital F for the antiderivative. Okay, so if lowercase f is used for the original function, then f prime is the derivative, and uppercase f is the antiderivative. All right, so let's try another one of these. So if you have your differentiation formulas in front of you, I bet you can figure out this problem on your own. First of all, the derivative of sine is cosine, right? So we have our derivative. But I bet that you can look at those formulas and you can probably figure out what the antiderivative is going to be. You do have to do some sort of modification. So if you want to try that, pause the video and see what you can do. We know that the derivative of cosine is sine. So we know cosine has to be involved. The problem is if we find the derivative of that, we get negative sign. Well, we don't want that negative there. There shouldn't be any negative there. So all we have to do is just counteract by writing a negative symbol in front of cosine. So now, when we find the derivative of negative cosine, we need to use the constant multiple rule. And the constant multiple rule is a rule number 3, this rule here. Rule number 3 tells us that the derivative of a constant times a function is equal to the constant times the derivative of the function, which is negative sine x. Again, the derivative of cosine x is negative sine x. So the negatives, when we multiply them together, we get sine x, and that's exactly what we're looking for. So this is not that difficult, but it does take some modifications to find the right antiderivative. So let me rewrite that. That's negative cosine x. Now, typically students have some problems with this because it's kind of hard to go backwards in your mind. Some students find this to be kind of challenging because, it's difficult enough having to learn how to find derivatives, but now we're going in the opposite direction. So it takes some thought, and if you're having trouble with this, that's okay. Every student has a little trouble with this when they first learn this. But we're not done. We need our constant plus c. Again, if you have negative cosine x plus 9 and you find the derivative of that, you get sine x, right? If you have negative cosine x minus 1 million, find the derivative of that, find the derivative, and you get sine x. So there's all kinds of different functions that could be the antiderivative of the original function. We say that there's a family of functions. Okay, so let's do some more of these problems. How about this one? Now we have a constant. So let's find the derivative of this. Well, the derivative of any constant is just 0. You know that. You've done this many, many times. But what about the antiderivative? Well, we don't have any x here. We don't have a variable, but we can just consider that to be x to the 0 power. And although it doesn't really make any sense to reduce the exponent by 1 to get to the derivative, because then you would have x to the negative 1 power. That wouldn't really work. That wouldn't give us the derivative. But it does work if you add 1 to get to your antiderivative. Remember, you do the opposite operation. Then we would get x to the 1 power. It's probably just best to memorize that the derivative of x is 1. Then we add c, and there you go. So again, 8x plus 10, the derivative is 8. 8x plus 13.3, the derivative is 8. There's all kinds of different functions. There's a family of functions that could be considered the antiderivative of the original function. Okay, let's try another one. So let's find the derivative. We're going to use the constant multiple rule. So we have negative 2 times 5x to the 4th power, or 5x to the 5 minus 1. And then we get negative 10 times x to the 4th power. You don't have to show this intermediate step. I'm just reminding you of the rules that we're using. We use the constant multiple rule and the power rule. So that's the derivative. Now let's try to see if we can find the antiderivative. Well, we subtract 1 from the exponent to find the derivative, so obviously we're going to add 1 to go in the opposite direction. Now here's the part where we have to stop and think, because we know the derivative of x to the 6th power is probably not going to be what we're looking for. That gives us 6x to the 5th power. So we don't want a 6, we want a negative 2. But we know that when we bring down the exponent, we're going to multiply it into the expression. So the question, I guess, is 6 times what number is equal to negative 2? And obviously the answer to that question is negative 1/3. If you solve that equations, negative 1/3. So what that means is we need to write a negative 1/3 in front of x to the 6th power. Now, if we find the derivative of this, we use the constant multiple rule. So you take the constant and multiply it by the derivative of the function. And negative 1/3 times 6 is negative 2, and that's exactly what we're looking for. Okay? So it just takes a little bit of trial and error to do this. It's not something that's tremendously complicated. Now, we can't forget to write our c value, right? We have to write our c value. Okay, on to the next one. So let's find the derivative. We're going to use the constant multiple rule. We have a constant, and then we're going to multiply by the derivative of the function, and then we get 10 times sine x. That's the derivative. But now we're going to find the antiderivative. So we know the derivative of sine. If you look at your trigonometric differentiation formulas, the derivative of sine is cosine. So we know we have to have a sine up here. If we find the derivative of that, we get cosine x, but we want a negative 10 in front of there. Well, in this case, we would just write negative 10 in front of the sine x. Find the derivative of that, and you just get negative 10 cosine x. So that was pretty easy. That we didn't really have to do any tricks for that one. And of course, we need to add our c value. Again, the antiderivative represents a family of functions. Okay. Let's do one more of these before you try one on your own. So I know that this seems like a variable, but it's actually a constant. Remember, we learned Euler's number. So the derivative of a constant is just 0. Now, if we go in the opposite direction, the derivative, or the antiderivative, is going to be e squared times x plus c. So if we find the derivative of this, obviously the constant just goes to 0. And the derivative of this, it's like if you had 3x, the derivative would just be 3, right? So here we have e squared x, the derivative is just e squared. Okay, so I know that's kind of weird, but that's how that works. So now I want you to get a picture of these formulas if you haven't already done that. You really need these formulas in front of you, and I want you to get a picture of all this information, and get a picture of this problem if you want to. And I want you to try number 7. So first find the derivative. You know how to do that. You've done it a million times. And then find the antiderivative. And remember to add c. Try number 7. When you come back, we'll do it together. Okay, we're back. Don't forget to write your plus c. Students often forget that. So if you got those answers, good. And if you're having trouble with this, then the only solution to that problem is just do more practice problems. That's the way it is with mathematics. If you're having trouble, do more problems. If you're still having trouble, do more problems. Practice problems are the key to you excelling in a math course, because the primary objective of a math course is to learn the language. Once you know the language, 85% of the objective of the course is really complete. Okay, so go ahead and try number 8, and when you come back, we'll do it together. Okay, we're back. So if you got that right, excellent. Okay, I want you to try number 9, and when you come back, we'll do it together. Okay, we're back. So if you got that right, excellent. Okay, now this one's a little tricky. It's a little tricky because you're going to end up with a fraction up here. So do your best. If you get stuck, that's okay. But go ahead and try number 10. When you come back, we'll do it together. Okay, we're back. Okay. So, if you got that right, excellent. That was kind of a challenge problem. Try number 11. When you come back, we'll do it together. Okay, we're back. And then we have to add our C. So if you got that right, excellent. Okay. Go ahead and try number 12. When you come back, we'll do it together. All right, we're back. So if you got that right, excellent. Okay, so now let's try this problem together. We have kind of a special function here. It's just x. Now, you know that the derivative of x is just 1. We've covered that quite a few times. I mean, the power is considered to be 1. So when you find the derivative, remember the power rule tells you to subtract 1, and then you get x to the, well, first you bring the 1 down, and then you subtract 1 from 1, and you get 1 times x to the 0 power, but x to the 0 power is just 1, so you just get 1. But it's not really practical to do this in your head every time you want to find the derivative, so it's better just to memorize that the derivative of x is just 1. Okay, now we're going to go backwards. So remember, the exponent here is 1, right? So if you subtract 1 from the exponent to get the derivative, we're going to add 1 to the exponent to find our antiderivative. But now, if you find the derivative of that, you get 2x. Well, we don't want 2x. We just want x. So we need to counteract by writing a 1/2 there. So there you go. So that is the family of antiderivative functions. All right, now here's kind of a weird example. We're going to find the derivative of 8 to the x power. I believe this is differentiation formula number 9, if I remember correctly. Yes, it's number 9. Finding the derivative of an exponential expression. It's just the expression times natural log of whatever the base of the expression was. So again, you should have those formulas right in front of you. If you haven't taken a picture, I'll give you one more chance to do that. So the derivative is 8 to the x power times natural log 8. To be honest, typically teachers don't really focus much on these functions when we're finding the derivative. But technically you are required to know how to find the derivative of that. So now, how are we going to find the antiderivative? I mean, there's an 8 to the x, so we know that we have to have 8 to the x in order to get 8 to the x when we find the derivative, right? But the derivative of this, as we just explained, is 8 to the x times natural log 8. Well, we don't want that. We just want 8 to the x. So how do we get rid of this? Well, natural log 8 is multiplied into the expression. What's the opposite of multiplication? The opposite of multiplication is division. So we can just multiply by 1 over natural log 8. Another way to think of it is you can write it like this, but that causes some confusion in the future. So usually we just think of it as multiplying by the reciprocal. So we're going to modify this with a 1 over natural log 8. So you can put the 8 to the x here, or you can put it up in the numerator. It's the same thing. It doesn't, however you want to do it. So now when we find the derivative, we use the constant multiple rule, which tells us that the derivative of a constant times a function is equal to the constant times the derivative of the function. And the derivative of 8 to the x is 8 to the x times natural log 8. But notice that these natural log 8s cancel out. And then you're left with 8 to the x. So there you go. So these are kind of some weird examples that you might encounter. Okay, let's have you try number 15. So I'm going to leave numbers 13 and 14 in the window. You can try number 15. And when you come back, we'll do it together. Okay, we're back. Again, e to the x plus 9, the derivative is e to the x. E to the x minus 20, the derivative is e to the x. So again, we need a constant represented there because we don't know what that number is going to be. So go ahead and try number 16 if you got 15 right. Excellent. Try number 16. When you come back, we'll do it together. Okay, we're back. So if you got that right, excellent. All right, go ahead and try number 17. You're going to want to use differentiation formula number 9. I'll leave number 14 in the window. That'll help you. So go ahead and try number 17. And when you come back, we'll do it together. Okay, we're back. So if you got that right, excellent. Okay, so let's try this next one together. Now we have a lot of terms here, but it's just going to be the same principle, just with more terms. So let's find the derivative. We've done this many times, so we know how to find derivatives. It's all just the same stuff. And so that's the derivative. And now we're going to use the power rule, but going in reverse. So we're going to add 1 to the exponents. And 1 actually becomes x. And then we're going to have to add a c, because there could be a constant. So we know when we find the derivative, the 6 is going to come down and multiply into something, and we get 8. But what is that something? Well, 6 times something is equal to 8. If you solve the equation, you get 4/3. So we need 4/3 there. And when we use the power rule, we're going to multiply 4 by something to get negative 20. Well, what would that be? Well, it's negative 5, of course. So negative 5. And then we're going to bring down the 2 when we use the power rule, and it's going to multiply into something, and we're going to get 3. So what would that be? Well, it would be 3/2. And then here, obviously, we're just going to we're going to have well, that is just going to be x. And then the derivative of c is 0. So let's double check, make sure we got everything right. Everything looks good. So this is a family of functions that represent the antiderivatives of this function here. Okay, so let's try another one. We have a sum of terms again. So the derivative of sine is cosine, and the derivative of this would bring the 8 down and reduce, and we get 8 over 60, which is 4 over 30, which is 2 over 15. And the derivative of e to the x is just e to the x, using the constant multiple rule there. So the derivative of a constant times a function is equal to the constant times the derivative of the function. Well, the derivative of the function is just e to the x. Now let's go backwards. So the derivative of cosine is negative sine. So we need a cosine there. When we find the derivative, we should have a negative. So that's gonna appear when we find the derivative of cosine. So all we need is a 7 in front of there. And again, you can always verify this stuff by just finding the derivative of whatever you write up here and seeing if it works. If it doesn't, you just modify it slightly. And then we're going to need x to the 9th because we have to add 1 to the exponent. We're going backwards. And when we find the derivative of this, 9 is going to come down and multiply into something, and we're going to get 1 over 60. So what would that be? Well, it looks like that would be 1 over 540 if we do the math on that. 1 over 540. Alright, and then the antiderivative of the next term would just be 5e to the x, and then we have 9x, and then we have plus c. So, again, you can confirm that this works by simply finding the derivative of the yellow expression, and you should get the blue expression. And if you don't panic. Just modify the expression a little bit. Okay, so you can take a picture of these problems if you'd like, and I want you to try number 20. Now we're going to need differentiation formula number 9 again. So consult differentiation formula number 9 and go ahead and try this problem. And when you come back, we'll do it together. Alright, we're back. If you got that answer, excellent. Okay, I want you to try number 21. Go ahead and attempt this problem. And remember, e is just a constant. That's Euler's number. So try number 21. When you come back, we'll do it together. Okay, we're back. And then we have to add our c value. So if you got that right, excellent. Okay, let's try this one together. Now, things are getting a little bit more difficult because we have an expression that takes a little thought before we do this. We can use the quotient rule. Remember the quotient rule. But most students don't really want to use that. So we're going to change the form of this to 5 times x to the negative 4th power. And now we can just use the power rule. So we're going to use the constant multiple rule. And then the power rule. And we get negative 20 times x to the negative 5th. The problem is, in my curriculum, I don't allow you to leave your answer with negative exponents. So we're going to change that to 1 over x to the 5th power using my exponent rule, number 8. So then we can write our final answer as negative 20 over x to the 5th. So I'm going to find the exponent rules for you in case you want to review those. So here are the exponent rules. We used this rule here, number number 8. So you may want to get a picture of those rules if you want to review those. So now we need to find the antiderivative. So again, focus on this expression here. We're going to add 1 to the exponent because we subtracted 1 to find the derivative. So that means we're going to have x to the negative 3 power. Now if we find the derivative of this, we get negative 3x to the negative 4 power. We don't want negative 3, we want 5. So what do you multiply 3 by to get 5? Well, that's going to be negative 5/3. So we need to modify this expression by writing negative 5/3. So now when we find the derivative of this, using the constant multiple rule, we get the following expression. The negatives cancel out, the 3's cancel out. We're left with 5x to the negative 4th, which is what we want. Okay, but there's two things that we need to consider. Number 1, we have to add our c value, and number 2, in my curriculum, remember, I don't allow you to leave your answer with a negative exponent. So you got to use exponent rule number 8 again and change the form of that expression. Alright, so there you go. So here's another example which is a little bit more intimidating. We don't really know how to find the derivative if we have a root. At least it's not exactly easy. So we're going to change to x to the 4/3 power. And now we can just use the power rule. So we get 9 times 4/3 times x to the 4/3 minus 1. And then we get 12 x to the 1/3 power, but remember, you're not allowed to leave your answer as a fraction power, so we have to change that to the cube root of x. Alright, so we subtracted 1 from the exponent to find our derivative. We're going to add 1 to the exponent to find our antiderivative, so that's going to be 7/3. 4/3 plus 1 is 4/3 plus 3/3, which is 7/3 as a common denominator. Now if we find the derivative of this, the 7/3 is going to come down in front, but we don't want 7/3, we want 9. So what can we multiply 7/3 by such that we get 9? And the answer is going to be 27 over 7. All you have to do is just solve this equation and you find the answer. We're modifying this expression up here by adding the 27 over 7. That way when we find the derivative, we're going to get this expression here. So you can verify that by finding the derivative using the constant multiple rule. We get that, and then the 7's cancel out, and 27 over 3 is 9, and there you go, 9x to the 4/3 power. Now again, in my curriculum, we're not allowed to leave answers with fraction powers or negative powers. So we need the cube root of x to the 7th. And there you go. Now you can also write that as the cube root of x all raised to the 7th power. Remember, there's two versions of exponent rule number 10. So just be aware of that. Okay. Let's try one more of these. So here's another weird problem where it's a little intimidating. It may not be exactly obvious how to do this. So we need to change the form of the expression because we don't really know how to find the derivative the way it is now. So let's use exponent rule number 9 to change that to x to the 1/2 power. By definition, that's just what that means, x to the 1/2 power. Then let's use exponent rule number 8 to bring that up to negative x to the negative 1/2 power. Okay, so that's what that means. Now we can use the power rule easily. So we have negative times negative 1/2 times x, and then subtract 1, and you get negative 3/2. You might wonder if it would be better to write a mixed number, and the answer is no. It's easier in upper math courses to use improper fractions than to use mixed numbers. Okay, so again, we're not allowed to leave our answer with fraction exponents or negative exponents, and we have those two problems. The first problem that we need to deal with is the negative exponent. So we used exponent rule number 8 there. Then we have to use exponent rule number 10 and change that to the square root of x cubed, and we can multiply these fractions, and there you go. So we had to subtract the exponent to find our derivative, or we had to subtract 1 from the exponent. We just need to go in the opposite direction to find the antiderivative, so we're going to add 1. If you add 1 to negative 1/2, you get 1/2. So now let's find the derivative of this, and we get 1/2 times x to the negative 1/2. So we have the right exponent, but we don't want a 1/2 there. We just want a negative 1 there. So again, the question becomes, we know we're going to bring down the 1/2 and multiply. So 1/2 times what number is equal to negative 1? And that's going to be, of course, negative 2. Alright, so we get negative 2x to the 1/2, and we have to add a c value, obviously. But remember, we're not allowed to write our final answer with a negative exponent or a fraction exponent, so we have to change to root x. Okay, so now it's time for you to try. So again, I'm going to give you one more chance to take a picture of these exponent rules, because you're really going to need these. Technically, you should know all these at this point in your math curriculum. Most teachers are not even going to show you those. They're just going to assume that you know them. But you're going to need them for problem 25. So remember, you're going to have to change the form of this first. So use exponent rule number 8 to change the form, and then you can use the power rule to find the derivative. So try number 25. When you come back, we'll do it together. Okay, we're back. If you got that right, excellent. Okay, go ahead and try number 26. Now again, we can't find the derivative of this directly. You have to change it so that we have an exponent. So try number 26. When you come back, we'll do it together. Okay, we're back. So if you got that right, excellent. All right, go ahead and try number 27. We have to change the form of this before we can find the derivative, or the antiderivative. So you're going to have to change this to a fraction exponent, and you're going to have to get it out of the denominator. So try number 27. Again, you can use your exponent rules. I'm going to give you one more chance to use your exponent rules. We're going to have to use rule number 10 and rule number 8. Attempt number 27. When you come back, we'll do it together. Okay, we're back. So there you go. Okay, so let's try this next problem together. If you got number 27 right, good job. Students get kind of confused by this. And the reason they get confused is because they think that you have to use the quotient rule. Remember, the quotient rule is rule number 7. If you're finding the derivative of a quotient or a fraction, you have to use this formula here. But that's if both of these expressions are functions of x. What if one of them is just a constant? Well, if one of them is a constant, you can modify the fraction so that it looks like this up here. Then you don't have to use the quotient rule. So that's something that students have to learn. And so I'm going to show you that right now. We're just going to change this to 1/6 times x to the 3rd power. Now we can easily find the derivative. So we get 1/2 times x squared. That is the derivative. So we use the constant multiple rule and the power rule. So now we're going to add 1 to the exponent to find the antiderivative. We subtracted 1 from the exponent to find the derivative. Now if we find the derivative of that, we get 4x to the 3rd power. We don't want 4x to the 3rd power, we want 1/6x. So when we bring this 4 down and multiply it into something, we should get 1/6. What is that something that we need to multiply it by? Well, that's going to be 1/24. So you can verify that when you find the derivative of this, you get this. And we need to add c, of course. So there you go. So again, no need to use the quotient rule here. Just use the constant multiple rule. So here's another example where students tend to think that they need to use the quotient rule. You don't have to. You can just factor out -2 over pi, and then you're left with 1/x squared. And then you can change 1/x squared to x to the -2 power using exponent rule number 8. So there you go. So now we're going to find the derivative using the constant multiple rule. The derivative of a constant times a function is the constant times the derivative of the function, which is -2x to the -3 power. So we have +4 over pi times x to the -3 power. We can't leave our answer like that. So we have to bring it down using exponent rule number 8. So we get 1/x cubed. And we can put those together and we get 4 over pi times x cubed. That's the derivative. Now we subtracted 1 to find the derivative. We subtracted 1 from the exponent. So now we just add 1, so we're actually going to get x to the -1 power. So if we find the derivative of this, we get -x to the -2 power. We've got the right exponent, but we certainly don't have the right coefficient there. So when we bring the -1 down, we're going to multiply it into some number. -1 times some number needs to be equal to -2 over pi. Because we want to get this expression when we find the derivative, not this expression. So what do we need to write here such that we get -2 over pi? Well, we simplify and we get +2 over pi. That was pretty easy, actually. Okay, so if we find the derivative of this, we get this expression here. But again, remember, we can't leave your answer with a negative exponent. There are some teachers that would allow you to do that, but it's not really appropriate to do that, because those expressions need to be translated into something that actually makes sense. Okay, so there's another example. Let's try one more of these before you try one on your own. So again, students would look at this and they would say, well, I have to use the quotient rule. Actually, you don't. You can just use the constant multiple rule. Find the derivative, and we get negative 1/5 sine x. Again, dividing by 5 is the same thing as multiplying by 1/5, so why would you use the quotient rule? It's so much easier to use the constant multiple rule. So the derivative of sine x is cosine x, so that's pretty easy. Okay, so now it's time for you to try. If you'd like, you can take a picture of these problems that we just did, and take a picture of this problem that we just did, and I want you to try number 31. So again, you have to rewrite this expression. You don't want to use the quotient rule. Instead of x to the fourth divided by 5, you want to say 1/5 times x to the fourth, and then consider the expression in that way. So try number 31. When you come back, we'll do it together. Okay, we're back. If you got that right, excellent. Okay, go ahead and try number 32. Now again, students are going to have a tendency to want to use the quotient rule, but you can write this in a way such that you can pull out this this negative 1/2. Now be careful, because the cube root of x is still going to be in the denominator of a fraction. So see what you can do. Try number 32. And if you get stuck, we'll do it together, but try number 32. When you come back, we'll do it together. Okay, we're back. So we got that right. Excellent. All right, why don't you try one more of those? Again, when you look at this, the tendency is to say, well, we have to use the quotient rule. But you don't, because this is just a constant. See if you can factor that out, so you don't have to use the quotient rule. You can use the constant multiple rule. Try number 33. When you come back, we'll do it together. Okay, we're back. So now, I know what some students are going to say. They're going to say, wait a second, that's not a rational denominator. Do we have to change that? Do we have to change that to root 2 over 2? You can if you want to, but in the calculus curriculum, generally, teachers don't really care. Now, you might say, well, wait a second, if teachers don't care, why did we have to learn how to rationalize the denominator? Well, mostly because there's a couple of reasons. Primarily because when you go out into the world and you see this expression turned into this expression, you have to know how that actually worked. You can't just be lost understanding how that changed. The second reason is that in school you will see that from when you first learned it in beginning algebra all the way up to your first calculus course. So again, it's just part of the language that you need to know. Okay, so now we're going to some interesting problems here. This is not going to be quite so easy to find the derivative. We have to use the product rule. because we have a function of x times another function of x. We have to use the product rule. So remember, the product rule tells us that if we have a product of two functions, and you can make this negative go with the cosecant, or you can make it go with the cotangent. It doesn't matter. But once you decide, you have to stick with that. So what we're going to do is we're going to find the derivative of negative cosecant x, and I'm going to show this. I'm going to show the formula. I'm going to show the process for you by writing d over dx, but I want you to understand that if you know how to use this formula, you don't have to show this. You don't have to show d over dx. You can just do it in your head and find the answer. But the formula tells us to find the derivative of the first thing in the product and multiply by the second thing. Then we're going to add the first thing in the product multiplied by the derivative of the second thing in the product. That's the product rule. And you might say, you know, as you said in probably previous classes, you might say, well, I don't like that. I don't want to do that. Well, nobody wants to do it, but that's just how you have to find the derivative of a product, or else your answer is going to be wrong. So the derivative of negative cosecant is, the derivative of cosecant is negative cosecant x, cotangent x. So we have to use the constant multiple rule. We have a constant multiplied by a function. So the derivative of that is the constant multiplied by the derivative of the function. And then we have negative cosecant x times the derivative of cotangent, which is negative cosecant squared x. So this became that, and all that became this. Oh, whoops. I forgot to write my cotangent there. Sorry about that. I didn't write that cotangent. Okay, so all we have to do now is just simplify. So we have cosecant x times cotangent squared x plus cosecant cubed x. So that is the derivative. So the bad news with that problem is that we had to use the product rule, and so it was fairly complicated. But we do have some good news. The antiderivative is actually going to be pretty easy. Oftentimes students are given expressions like this and they're asked to find the antiderivative, but it doesn't look like it's going to be very easy. It looks like it's going to be really, really difficult. And in most cases, when you have a product of two functions like this, you would have to use principles that you're going to learn in the next calculus course, to the point where we couldn't even do this, right? But it just so happens that this is a special expression. Look at your derivative formulas for trigonometric functions. The derivative of cosecant x is just negative cosecant x times cotangent x. So that's just like a trick problem. It looks like it's going to be really hard, but you just have to know your differentiation formulas. All right. So let's try another one here. This is kind of another trick problem. It's a tricky thing here. A lot of students would look at this and say, "Well, I need to change it to an an exponent." Oh, we have 1 over x to the 1 power. Using exponent rule number 8, we have x to the negative 1 power. All right. And when I find the derivative, we just use the power rule. So we get negative x to the negative 2 power. Use exponent rule number 8, and we end up with negative 1 over x to the 2nd power, and that's correct. So we've done everything correctly so far. But here's where the problem comes in. Try to find the antiderivative. Strange things are going to happen. So remember, you subtract 1 from the exponent to find the derivative. If we add 1 to this, well, we get x to the 0 power. So x to the 0 power is just 1. So a lot of students would say, well, okay, what's wrong with that? Well, what's wrong with that is if you find the derivative of 1, you don't get 1 over x, you get 0. So obviously that's not correct. So this is kind of a special situation. So what I want you to do is look at this expression here and go to your differentiation formulas. Can you find a function such that when you find the derivative, you get 1 over x? Find a function such that when you find the derivative, you get 1 over x. That's going to be right here. So it's a trick. It looks like it's not going to be solvable, but actually it's really easy. The answer is just going to be natural log x. So the antiderivative of 1 over x is just natural log x, and we just have to add a c. All right, so again, these are tricks. They're trick problems. It looks like you're not going to be able to figure out the answer, but actually we can figure out the answer. Here's another example. And so I've given you clues here as to what to do. And today we have not used the chain rule. When you find the derivative, you're going to have to use the chain rule. And remember, secant squared x is the same thing as secant x to the 2nd power. That requires the chain rule. Now, if you forgot the chain rule, you can join the club of most students, because they typically forget how to use the chain rule. They don't like the chain rule. They don't want to use the chain rule. And so if you forgot how to do it, that's okay, but see if you can remember how to do it. Remember, there's 3 steps of the chain rule. Find the derivative of the outside function. That's number 1 step. Step number 2, find or keep the inside function. And then step number 3, multiply by the derivative of the inside function. Okay, so and then when you find the antiderivative, well, that's going to be really easy. You just look at your differentiation formula. So go ahead and try number 36. If you get stuck, that's okay, but give it a try. And when you come back, we'll do it together. Okay, so we're going to find the derivative. So that's it. It's that simple. So again, it's a trick. It looks like finding the antiderivative is going to be impossible, but actually it's not. So now I want you to try this problem. And again, I've given you a clue. So look at differentiation formula number 9. And see what you can do with this problem. If you get stuck, that's okay, but see what you can do. And when you come back, we'll try it together. Okay, we're back. So it's that simple. It looked like it was going to be really difficult, but it was actually not difficult at all. If you got that right, excellent. If you had a little trouble with that, that's okay. Again, we're going backwards. We're going backwards from what we usually do, so going backwards is confusing. All right? So, again, students are going to have a tendency to want to use the quotient rule. Don't do that. Change to 1/4 cosecant squared x. Now we find the derivative, and it looks like we're going to have to use the chain rule. So I'm going to have to change that to cosecant x squared. We have a function that's inside another function. All right, so when we find the derivative, I'm going to have to use the chain rule. First, I'm going to use a constant multiple rule. And I'm going to find the derivative. We find the derivative of the outside function. Derivative of the outside function while we keep the inside function. And then we're going to multiply by the derivative of the inside function. That's the chain rule. So you can't escape the chain rule. You're going to have to use it over and over and over again. It's not going to go away. So 1/4 times 2 is 1/2. And then we have cosecant x, and derivative of cosecant x, that's going to be negative cosecant x times cotangent x. Okay, so then we have negative 1/2 cosecant squared x times cotangent x. That's the derivative. That's the hard part. The easy part is finding the antiderivative, because the derivative of cotangent x is negative cosecant squared x. So we know that we have to have a cotangent x up here somewhere. Again, look at your differentiation formulas for trigonometric functions. But when we find the derivative of this, we get negative cosecant squared x. Again, look at your formulas. We don't want a negative 1 in here, we want a positive 1/4. So we have to modify that by writing negative 1/4 there. Now, when we find the derivative, we use the constant multiple rule, multiply the constant by the derivative of the function, the negatives go away, and you're left with 1/4. That's what we want. So that is the antiderivative, and we have to add c. Okay, so let's try one more of these together. This really doesn't look pleasant, but if we take the negative 5 out, or factor it out, and then we consult our differentiation formulas, we can see that this is just the derivative of log base 3 of x. So that's one of the differentiation rules. But before we do that, we're going to have to factor out the natural log 3, because first we need to find the derivative. So I'm going to factor out negative 5 over natural log 3. We need to factor out natural log 3, not natural log x. But so then we're left with this expression here. And we need to change that to x to the negative 1 power. And now let's take the derivative. So using the constant multiple rule, we have negative x to the negative 2 power. And that will be 5 over natural log 3. And use exponent rule number 8, of course. And there you go. You don't want to write a multiplier in front to the right of the 3, because that could confuse things. So it's better to put the x squared in front of the natural log. Okay, so now let's find the antiderivative. Well, that's going to be the easy part, but we have to modify this a little bit. Now we're going to have to factor out the negative 5. So we use this expression here to find the derivative, but we're going to use this expression to find the antiderivative. this expression is going to be negative 5 times 1 over x natural log 3. So let's consider this expression here, and we'll look at exponent rule number 11. So we have 1 over x times natural log of something. In our example, we have 1 over x times natural log of 3. So the antiderivative is going to be log base 3 of x. So log base 3 of x and we need a negative 5 in front, so we can just write that negative 5 there, and it looks like that's going to be it. So the form that you write depends on what you're trying to find. Are you trying to find the derivative, or are you trying to find the antiderivative? To be honest with you, we really don't use these problems much in calculus. Finding the derivative of a logarithm, it's not really very common in the calculus curriculum unless you're finding the derivative of the natural log function. We find the derivative of that quite a bit, but we just don't really tend to use other bases other than base e. Okay, so now it's time for you to try. Again, these are kind of tricky problems. So you can get well, I'll leave this in the window, and you can try number 40. So I've given you hints here. Again, the antiderivative should not be that difficult to find. You just have to use your differentiation formulas. But the derivative is actually going to be kind of involved, because we have to use the product rule on this problem, and we actually have to use the quotient rule on this problem. We haven't used the quotient rule today, so let's see how you do on that. But first, let's try number 40. Attempt number 40. When you come back, we'll do it together. Alright, we're back, and now let's find the antiderivative. The antiderivative is going to be easy, and you can verify that by simply finding the derivative of this expression, and you should get this expression here. Okay, if you got that right, excellent. Let's try 41. So 41 is going to be a challenge problem. Now, I've given you some hints here. You're going to have to use differentiation formula number 13. We have not used that formula today, but you're going to have to use that. You're also going to have to use something that we have not used today, and that is the quotient rule. So see if you can do this. It's a challenge, but if you get stuck, that's okay, but you need to give it an honest attempt. So try number 41. When you come back, we'll do it together. Okay, we're back. So that is the derivative. That was kind of a challenge problem because we had to use the quotient rule. The quotient rule will show its face every once in a while, so you have to be ready for that. So now we have to find the antiderivative. Our formula tells us, formula number 13 tells us that if you want to find the derivative of a natural log function, the derivative is the derivative of the function inside the natural log divided by the function inside the natural log. That's exactly what we have down here. So that was kind of a tricky one, but that is your answer. So if you got stuck with those, that's okay. It's not a big deal. That was kind of a challenge problem. But if you got that one right, you should get extra credit for that. Now we're going to learn something called indefinite integrals. And without going into all of this stuff here, I'm just going to show you very simply what this means. You can obviously get a picture of this for your notes later on at the end of the class. We'll take a picture of that, but we've been finding the antiderivative of a function, but we have not been using the typical notation that you use to find the antiderivative. Now we're going to learn the notation that you actually use to find the antiderivative, and that is this symbol here. And we also have the symbol here. So it's actually two symbols that enclose the function that we're finding the antiderivative of. So what this expression means is find the antiderivative of this expression. That's all it means. Again, this is the typical notation we use. But we call this an indefinite integral. That's just the name that we give to it. Whenever you see an S symbol like this, that means integral. It's either an indefinite integral or a definite integral, but we're not going to learn definite integrals today. We're just going to learn what we call indefinite integrals. So again, it's just telling you to find the antiderivative. So that's just going to be 1/3 x cubed plus 28x squared plus 3x. And of course we have to add a c value. So there you go. So is that the antiderivative? Well, just find the derivative of this and see if we get back to this blue expression here. And you can see that we do. So there you go. So it's the exact same thing that we did in the previous problems, no difference whatsoever, except we learned this new notation. When we want to find the antiderivative of an expression, we enclose that expression, in this case the green expression here, inside the yellow S symbol and the dx. That's just how we notate that. And we call this an indefinite integral. Now, why do we call it an indefinite integral? It's indefinite because we don't know what c is. This actually represents a family of functions because c can be any value. So we call it the indefinite integral. Also, it's a function of x. So it's not an actual number. It's just a set of operations that will help you maybe find a number if you use this for something. Now, in the next class, we're going to learn definite integrals. A definite integral has the same S symbol, but a definite integral actually gives you a number. This is not a number. This is just a set of operations that tells you how to perform the operations. So again, we call this an indefinite integral, this expression here. So let's try another one. It's just asking you to find the antiderivative of negative 227. Well, that's just going to be negative 227x plus c. That's it. The antiderivative of x squared, or the antiderivative of x is 1/2 x squared. And then the antiderivative of negative 8 cosine x is negative 8 sine x. And again, you can confirm that just by finding the derivative of this expression and seeing if you get the blue expression. That is the antiderivative of x minus 8 cosine x. Let's try another one. Now, remember, we can't do this unless we change the form of these expressions so we can understand what's going on. So that's actually going to become 3x to the negative 3/5. Now, I'm not showing every step of that, but we're just using exponent rule 10 and number 8, and we're also factoring out the 3. That's just like a coefficient. Then we're going to factor out 9/4, and we're left with 1/x there. And so we have not found the antiderivative yet. We have not found the antiderivative. Now again, this dx just kind of floats out there. I know that's kind of weird that you have a dx just floating out there. It looks like the dx is multiplied by the 3e to the x, but it's not. It's just an ornament. This symbol and this symbol together, they enclose what we're trying to find the antiderivative of. So the dx and the s symbol are just ornaments. Don't consider this to be dx times 3 to the ex. Now there are some situations where you are going to consider the dx to be multiplied, but not right now. Not now in the curriculum. Okay, so now let's find the antiderivative. We're going to add 1. Remember, if you find the derivative, you subtract 1. We're going to add 1, so we get x to the 2/5 power. But if we find the derivative of that, the 2/5 is going to have to come down and multiply into something such that we get 3, right? So solve this equation and we get 15/2. So it looks like the coefficient has to be 15/2. Now, it doesn't look like we can find the antiderivative of that, but remember, if you look at your differentiation formulas, we know the antiderivative is natural log x. And remember, the derivative of e to the x is e to the x, so the antiderivative is just going to be e to the x. And so we just have one more step to go. Remember, we can't leave our final answer with a fraction exponent, so we're going to change that to the 5th root of x squared. So there you go. Okay, so again, all we're doing is just finding the antiderivative of the expressions. It's just different notation to find the antiderivative. So you can take a picture of this information if you'd like. And I want you to try number 46. So what is the antiderivative of x to the 9th power? That's all that's asking. What is the derivative of x to the 9th power? Again, this symbol and this symbol are just part of the notation. Those symbols are telling you that we're trying to find the antiderivative of this inner term here. So go ahead and try number 46. When you come back, we'll do it together. Okay, we're back. You can also write that as x to the 10th power over 10 plus c. It's the same thing. So if you got that right, excellent. Okay, go ahead and try number 47. So we're just trying to find the antiderivative of this expression. When you come back, we'll do it together. Okay, we're back. If you got that right, good. So remember to write your c values. Remember, we have a constant. We don't know what that is. Okay, go ahead and try number 48. When you come back, we'll do it together. All right, we're back. If you doubt that that is the antiderivative, all you have to do to confirm is just find the derivative of this, and you should get the blue expression. So I'm going to go ahead and do that in my head right now, because you always want to check your answer, and it looks correct. So this was the hard part there. That kind of gets a little weird for students to think about. You have to write a fraction there. So go ahead and try number 49. When you come back, we'll do it together. Okay, we're back. So find the derivative of that and confirm that the derivative is this blue expression. So if you got that right, excellent. Go ahead and try number 50. Okay, we're back. So the antiderivative is pi cubed times x plus c. If you got that right, excellent. Again, pi is just a constant. So now you need to look at differentiation formula number 9 for this one. That'll help you quite a bit. When you come back, we'll do it together. Okay, we're back. If you use the differentiation formula, that was an easy problem. But if you didn't, that may have been a little a little challenging. So try number 52. When you come back, we'll do it together. All right, we're back. If you got that right, good. Try number 53. Look at your differentiation formulas, specifically the trigonometric ones, obviously. Try number 53. When you come back, we'll do it together. All we're trying to do here is find the antiderivative of this expression. That's it. Now, this is a trick. It's a trick. It looks like it's going to be really difficult, but it's actually not if you look at your differentiation formula. So try 53. When you come back, we'll do it together. Okay, we're back. So again, if you doubt this, you just find the derivative of this expression, and you should get this expression in here. So there we go. So that was the class today. When you see this S symbol and this dx and an expression in between it, all that means is that you're trying to find the antiderivative of that expression. So you're going to see that notation thousands and thousands and thousands of times in the future. All right. If you'd like to take screenshots of all the work that we did to help you with your homework or to study for tests, go ahead and do that now. Here's screenshot number 1, number 2, number 3, and 4, and 5, 6, 7, 8, 9, and 10. But don't go before you get your homework. Remember, the homework is not optional. So take a screenshot of this first page of the homework, and this screenshot, and this one, and this one, and the last screenshot there. But don't go before you get the answers. You have the start of the homework answers at the right, and then you have the remaining answers. Remember, it's not enough just to attempt the homework. It must be done correctly. So do that homework completely correctly and neatly, and keep it in order in your binder. And I'll look forward to seeing you in the next class.